Thank you. Yep, we already saw this a little bit. Happy to talk to you guys today, and thank you for sticking around for one more talk or a few more talks in the last session. We already did see the opening slides, so I'll step through if this is working. It is, okay. So this is some work that actually started back with the Rise 2 survey team and has continued into the ARDVARC P-STAR project that I've been PI of. And while we haven't been to Lunar South Pole just yet, we have been able to simulate a little piece of it in the Cinder Lake crater field just outside of Flagstaff. This is a big picture of one of the long shadows you get out there when we're doing the tests, which Alicia gave us a good intro to as well. So what inspired this work was sort of the general Artemis timeline. And this is a bit of an older slide, but it still checks out, where you see sort of where we are now with some robotic deployments leading up to eventually human presence on the lunar surface. And our idea was, what could we do with these precursor robotic assets? What data could we collect that would assist astronauts when they get to the surface in terms of data visualization and navigation? So for our purposes, we simulated a precursor rover that collected LiDAR data along with a few other data sets. So that way we could then return to the same field site with analog astronauts and do some data visualization in real time with augmented reality. So in order to do this, we needed three things. We needed a good analog field site. We also needed a good analog rover mission. And then finally, we needed some intrepid volunteers to be our astronauts in the field. And we were fortunate enough to get all three. The first was the easiest to come by because back in the 60s, NASA went ahead and created a field site for us. I think this is mentioned a couple times, but we have the video here. Actually, this is on YouTube. So if you want to look this up, it's the Cinder Lake Crater Field Generation. They filmed the whole thing, actually. So there's a lot of really good footage of its creation. But this is based on a lunar orbiter image. So they created craters with different amounts of TNT that exploded to recreate a section of the lunar surface in essentially 1-to-1 scale. And so we went out there at night using, as Alicia mentioned, a couple different light sources to illuminate the field. You can see a good picture here. We have those dark shadows in the craters and the long shadows extending from positive topographic features. And then if you look at it from above, this is a drone image from our 2024 field deployment. If you squint and kind of ignore the trees and grass, it could kind of be the lunar South Pole. And if you look very closely, in this little red dot is our rover making its way along. So this rover we borrowed from our friends at Mission Control Space Services up in Ottawa, Ontario. It had a bunch of different instruments mounted to it, but for our purposes, the most important was the LiDAR unit. This is a Leica BLK 360 capable of collecting millimeter precision point clouds. And so as the rover traversed the field site, it would stop periodically to collect point cloud scans. So this is just a snippet of our data. Each of the green cubes represents a location where the rover paused and took a LiDAR scan, and then they've been stitched together here. So it's very dense. You end up with a digital train model point cloud, which we can then use for the meat of this talk, which is the augmented reality data visualization. So we went back this year, 2025, with some volunteer astronauts, and we made use of the Apple Vision Pro augmented reality headset. It's a very powerful tool that not a lot of folks have used in science just yet. It's being adapted into industry, but it has a number of sensors, some very high resolution cameras and built-in LiDAR sensors, so it can sense the world around it, which is key for us because we have this digital representation of the field site. In theory, this headset should be able to recognize where it is based on the terrain it is sensing. We paired that with Goddard's Merit software, which is the mixed reality exploration toolkit. That's been developed by the ARVARC group at NASA Goddard, primarily for data visualization of different atmospheric data, some terrestrial data, as well as spacecraft development processes. And up until now, it had only been available for Windows, so we kind of forced the team to make the jump over. And it also presented quite a few challenges for us. So not just the software, but the hardware as well. For software, making the jump for any software from one operating system to another is a bit tricky, and particularly for something that hasn't really been done before. This was a good challenge to tackle, and I am forever thankful to the team for making it happen. But in terms of the physical space, we had two big challenges. The lighting environment we specifically chose to be a difficult thing for humans to navigate, but this is also difficult for the cameras and the LiDAR sensor, well, mostly the cameras, to figure out where they are on the headset unit. And then also, these are units that are designed for use indoors, primarily on the couch in your apartment, watching movies or browsing the internet. And we were forcing them out into a field site that was hundreds of meters along. So while it was very good at tracking its position, we were kind of pushing the limits of how far it could keep its internal position tracked. But moving on to the test, we met those challenges and did a series of traverses out at the Cinder Lake Crater Field. We see them here. This is a hillshade model of the area. Each of the traverses is about the same length, but had different assets or aspects that we were testing. The first one, shown in blue, was sort of our control test. This was just a paper and pencil traditional traverse. 3 stations. Our astronauts were asked to take a map book, which is similar to what they're using to train the Artemis astronauts. This is an example of a page from that map book. It has a couple different data sets you can look at with a grid, so you can relay your position, as well as the traverse path, and then a list of steps to follow in that traverse. And so, yeah, fairly simple standard field geology. You can see Jose Hurtado here standing by one of the big craters holding that physical pen and paper style traverse. And then we have another picture of, I think it's Alan, yep, looking at a rock, just holding that binder. So you have a physical object to reference, pretty standard stuff. And we did this so we could compare it to our second style of traverse, which we called AR Light, Augmented Reality Light, where we did a similar 3-station traverse, same distance out and back. But this time, instead of a physical map book, we had our astronauts wear the Apple Vision Pros, and they had access to a digital version of this. And the best video clip I had of this is actually from when we were setting it up. So I'll jump to that. So it's daytime in this video, but we use this at night, and you're essentially seeing the off-the-shelf software. You're able to look at the PDF, place that PDF wherever you want in your field of view, so you can make reference to it, but can also reach down and interact with the geology, scroll through the pages. So you're augmenting your experience in the field in a very basic way, but it gets you to be hands-free, and you're relying on that video pass-through to see the world around you. This version, we also had, thanks to Jared Roletta, who's at NASA Goddard, the ability to scan a rock with an XRF unit. And some of the work that he's done allows via Bluetooth magic, the data to be sent from that unit directly to the headset. So you can scan a rock and then in near real time get a ternary diagram just in your field of view. So it's getting towards that sci-fi era where you can scan a rock and find out what it's made out of and just keep going with your EVA. The third of our EVA traverses we called full AR, and this was really meant to be the test of our navigational aids. And so what this looks like is the field in front of you, but the traverse path is actually laid out in 3-dimensional space. Our video example here might be a little shaky, but hopefully it works. This is an example from night. We actually did end up switching this style of traverse testing to daytime to help the cameras track a little bit better. But at night, what you're seeing here is this blue pipe, which represents the traverse path. The green dots are a heavily decimated version of that rover point cloud, which is referencing the terrain. So that, in theory, matches with the terrain that's out there. And it's helping the Apple Vision Pro unit track with both its cameras and its LiDARs the real terrain and trying to match it with the previously scanned terrain. And then when you get to a waypoint, you see this big red pin, so it's very easy to find. And the idea here was that the astronauts would offload some of that mental capacity from trying to figure out where they're going with just dead reckoning and pace counting to be able to see those pins, walk directly to them, and then do more geology along the way. The other benefit here is with that point cloud sort of overlaid on the terrain, you can sort of see some hazards that you wouldn't be able to make out with the naked eye. And I see I'm low on time, so I'll just run through our simple conclusions that we have so far, some of the results. We had each of the participants wearing a GoPro camera, so we have video and audio recording of each of these traverses, as well as GPS. We have GPS unit on their vest as well. So for the paper and pencil traverse, people were able to complete the traverse, but it was a bit nebulous. You kind of get to the spot, but using dead reckoning, there's always going to be a little bit of an error. For the light AR, it was a similar situation, sort of a vague cloud. But then, as you can imagine, if you have a line to follow and some pins to walk towards, everyone's traverse paths sort of converge. So this is showing that you can do a bit more precision EVAs with this tool. And there's a few takeaways. The first two are sort of a double-edged sword. Yes, it does enable this more accurate positioning, but it does kind of give a sense of tunnel vision where you're sort of just following the traverse, and additional training would be needed to enable folks to sort of explore naturally, but then get back to the path that they might need. And then just to end it, even the simple AR is it's a great tool for basic terrestrial geology, and we're just at the tip of the iceberg right now. I have probably out of time, so good. Well then, so looking ahead to the future, this is what we're developing now. It's sort of the mission control side of this. So this is a PC just observing the Merit software, and it's getting the location data from the headset relative to the digital version of the terrain. So essentially, you can track the location of an astronaut based on the position of their headset in the pre-scanned terrain. And so you have pretty accurate location data. And the Apple Vision Pro is very good at tracking hands as well. So eventually we'll be able to not just track position of the astronaut, but what their hands are doing at the same time. And so I'll end by saying a famous quote: "Not all those who wander are lost, but especially if you have AR data to get you back on track." Thank you to the team.